So far, we've only been looking at reactions of benzene itself. Benzene has only hydrogens attached. We're now going to look at what happens when we use an aromatic ring that has groups other than hydrogens attached to the benzene. We're going to call these groups substituents, and we're going to first talk about the substituents themselves, and then we're going to talk about how they affect the reaction in the aromatic electrophilic substitution. So first of all, let's talk about the substituents. We're going to classify the substituents based on how they affect the electron density of neighboring atoms, particularly the atoms in the aromatic ring. We can basically divide these into two effects. Electron donating groups increase the electron density of neighboring atoms when compared with hydrogen. We really haven't encountered many of these, but one that we have looked at in the past are carbon alkyl groups, where we saw that they stabilized adjacent carbocations. Electron withdrawing groups are actually the E groups that we talked about in the Diels-Alder reaction earlier this semester. The electron withdrawing groups decrease the electron density of neighboring atoms, or in this case, the aromatic ring, when compared to hydrogen. Now, there are two ways that groups can have these type of electronic effects. The first way is called the inductive effect. Inductive effects occur by donation or withdrawing of electrons through sigma bonds, through single bonds. These generally relate to electronegativities and the presence of partial minus or partial plus charges on the bond itself. So when we looked in first semester at bond polarity is generally a really good example of an inductive effect. A really good example of an inductive group is the halogen. Halogens, because they have high electronegativities, they're really common inductive electron withdrawing groups. We can see that when we look at a structure like this alkyl halide right here, where because the chlorine has a very high electronegativity, it is pulling electrons through that single bond away from the carbon. So the bond is a polar covalent bond, so that the chlorine N gets a partial negative charge because it has a slight excess of electrons, and the carbon has a slight positive charge because it is lacking electrons. Carbon groups, as I mentioned earlier, are really common inductive electron donating groups. So for example, if we compare a methyl cation, carbocation, to a T-butyl carbocation, what we see is that the T-butyl, because it has more carbon groups directly attached to the positive carbocation, is more stable. Those carbon groups are pushing electrons through the single bonds toward the central carbocation, and as a result, the carbocation is not missing as many electrons. It makes it happier, in other words, more stable. Tertiary carbocations are more stable than primary. The other type of electronic effect that we see is the resonance effect. Resonance effects occur when electrons are donated or withdrawn through pi bonds. So for example, we saw in an earlier chapter that allylic carbocations are really more stable than typical carbocations, because when they have this adjacent pi bond, that adjacent pi bond can use resonance to push electrons toward the carbocation, effectively creating a new pi bond and delocalizing or changing the position of the carbocation. What we see in general is that resonance effects tend to be stronger than inductive effects, and we're going to see this when we see them in conflict with each other. The next thing we want to look at is, how do substituents affect the reactivity of the benzene ring? What we can do is we can take a benzene, react it with a given electrophile, and then measure how quickly is the product formed. We would call that the rate of the reaction. Because this is a reaction with only hydrogens, we might write rate parentheses, hydrogen. What we could then do is replace one of the hydrogens with some type of different group. So this could be an alkyl group like methyl. It could be a halogen. It could be a nitro group. There's a number of different groups that it could be. We're going to use the symbol G in a circle to represent that substituent group. We're going to use the same electrophile, measure the reaction rate, and we would call this the rate with that substituent. And what we want to do is compare. How is the rate with the substituent when compared with the rate of the hydrogen of benzene itself? If the substituted aromatic ring reacts faster than benzene, then we call the group an activating group. Activating groups make the aromatic ring react faster than benzene. If the substituted aromatic ring reacts slower than benzene, then the group is a deactivating group. Deactivating group make the ring react slower than benzene. Now, how can this occur? Well, when we looked at the reaction energy profile earlier in this chapter, we saw that the first step is the rate determining step. So in order to make the reaction faster or slower, something must be occurring to the transition state of the rate determining step. So what I've drawn here is a comparison of how the reaction energy profiles might look depending on whether there are substituent groups attached and what type of substituent groups are attached. Let's start with the black energy profile. This is the energy profile for benzene itself, where there would be no substituent, there would be only hydrogens. We could see that the rate determining step would look like this. It would start low, it would come up over a transition state, it would come down to an intermediate, and that intermediate is essentially the delocalized carbocation. If we look then at having an electron donating group attached, I've written that in blue, we would start with this reactant. It would start at essentially the same potential energy of benzene itself. It would come up over a transition state and it would come down to an intermediate that would look like this, where we would have the carbocation, but then we would have a donating group attached onto that carbocation. As we discussed earlier, donating groups are going to stabilize the carbocation. Now, because of the Hammond postulate, which we discussed in a chapter in first semester, the Hammond postulate says that if we have an elementary reaction, and that elementary reaction is endothermic, then the structure of the product is going to look very similar to the structure of the transition state. The significance then is that if we compare these two products, the product from the black reaction energy profile, which is just benzene, and the product from the blue one, which is where we had a donating group attached, we can see that the blue energy profile has a product that is lower in energy than the black energy profile. We would therefore expect about a similar difference in energy between the transition state of the black energy profile and the transition state of the blue energy profile. Why? Because this transition state looks like this intermediate product. The blue transition state looks like the blue intermediate product. So if these two intermediate products are separated, the two transition states should be separated. The result would be that the blue energy profile would have a lower energy transition state, which means it would have a smaller activation energy. We would have a faster reaction. If we look instead at having electron withdrawing group attached, we would get the green energy profile. Again, we would start at about the same energy. We would go up over a transition state down to an intermediate carbocation product. In that case, however, the carbocation with an electron withdrawing group would become less stable. That would raise the energy of our green intermediate product. Again, by the Hamilton postulate, by the Hammond postulate, we would see that the transition state would also go up. That would make a larger activation energy. That reaction would go more slowly. This is explained in the text below. You can read it. We're now going to look at the regioselectivity effect of substituent groups. We're now going to discuss the effect that substituent groups have on the regioselectivity. In other words, which constitutional isomers are we going to get from this electrophilic aromatic substitution? Now, when we do this on benzene, because all of the six carbons have hydrogens on them and they're all identical, it doesn't matter where the electrophile goes. But when we do this on a substituted benzene, the substituent group provides a point of reference. So in this example, we can see that starting with this generic substituted benzene reacting with an electrophile, we would get three different possible constitutional isomer products. One where the electrophile group attached or replaced a hydrogen on a carbon directly adjacent to the group. One where the electrophile replaced a hydrogen on a carbon 2 carbons away from the substituent group, and then one where the electrophile replaced a hydrogen on a carbon opposite. So in relative numbering, starting with the group as number 1, this would not necessarily be the nomenclature numbering, but just saying, starting here as a point of reference, 1, count over 2. This would be the 1,2 constitutional isomer. We call this the ortho. That's an old-fashioned naming system. Relative numbering 1, 2, 3 then would be the meta, and 1, 2, 3, 4 would be the para. Now, there are actually two different orthos in theory because this carbon here is also 1, 2 related in the opposite direction. So that would also be ortho. And there's also two metas. There's only one para. Now what we're going to do then is we're going to make the assumption that the fastest formed intermediate will lead to the preferred product. So we want to find the pathway with the lowest energy transition state in step 1, and that should give us the structure of the preferred constitutional isomer. Again, we're going to use the Hammond postulate comparing the structure of the carbocation intermediate that's formed and use that to interpolate the relative energies of the transition states. This is shown for resonance donating substituents right here. So first of all, I want to point out that what we're going to do is a resonance donating substituent. A resonance donating substituent is going to have a pair of electrons on the atom directly attached to the ring. So we're going to represent that with a lone pair. But when we look at these in general, we will also see that carbon-carbon pi bonds can also do this. We're going to start then by looking at the intermediate structure that we would get by attaching the electrophile in the ortho position. So that would be right here. In the meta position, which would be right here. And in the para position, which would be right here. So going back to our generalized mechanism, if we take this pair of electrons, we make a bond to that electrophile, we put the electrophile here, we get a carbocation on the adjacent carbon, which I've indicated right here. And then we would have resonance. And you can see that what the resonance does is it delocalizes the carbocation to alternating, in other words, every other carbon around the ring. So here we are at what we might call the 4 o'clock position. It jumps over here to the 8 o'clock position, and then it jumps over here to the 12 o'clock. So we get 4, 8, and 12. Now the interesting thing about this is that the 12 o'clock position, as we have it written, is the carbon that has the substituent group attached. And that group has a pair of electrons. So that pair of electrons can move down into the empty space and make an additional resonance structure. And this is actually a really good resonance structure because we can see that all of the atoms should now follow the octet rule. When we talked about major and minor resonance structures, we talked about how following the octet rule is a really good thing. If we compare that to the meta, we would just put the electrophile at the other position. So then the carbocation would be here at 2 o'clock. Then moving it around using allylic resonance, it would move over here to 10 o'clock. And then it would move down here to 6 o'clock. And what you'll notice is that it never ends up in the 12 o'clock position, which has the group attached. So there is no opportunity for this additional, very stable resonance structure in the meta. If we look at the para, we can see a similar thing happening to the ortho. I've decided to use this double bond that I'm indicating right there. I attach it on the para. The carbocation is here. That would be the 8 o'clock position. We can move it to the 12 o'clock position. We can make the extra resonance structure. Then what we can do is we can also branch off from this resonance structure and move it to the 4 o'clock position. I've crossed out this arrow. I have it coming directly from there. So what's the conclusion here? Well, what we would conclude is that the ortho and the para constitutional isomers have an additional highly stable resonance structure, and the meta doesn't. So what that should do then is the ortho and the para transition states should be very stabilized, and the meta would not be as much stabilized. So if we look then, right here, this is what the reaction coordinates would look like. So we're going to compare to benzene. We're going to see that really we probably expect both the meta, the ortho, and the para to all be lower energy than benzene because donating groups are activating groups. However, the meta goes down only a little bit, whereas the ortho-para go down a lot because of the extra resonance structure. That's going to make their transition states much lower, so those two pathways are going to react much faster, and therefore we should get more of the ortho and para products. They would be preferred. Looking at the meta example, we have a similar diagram of the intermediates. Now what we're going to be doing is assuming that the intermediate is an electron withdrawing substituent. It's going to be pulling electrons away. So again, we attach on the ortho, we get the carbocation at 4, resonance delocalized to 8, delocalized to 12. And when we look at this 12 o'clock structure where the carbocation is directly adjacent to the electron withdrawing group, we can see that the electron withdrawing group is pulling electrons away from a carbocation. That's a very bad thing. It raises the potential energy because the carbocation is already missing electrons. It doesn't want to have to give away more electrons. So this resonance structure is very unstable. In the meta, again, we skip that 12 o'clock position. So the meta doesn't have a very unstable resonance structure. In the ortho, again, we go 8, 12, making a very unstable resonance structure, and then 4. So again, to summarize, the ortho and the para, they both have a very unstable resonance structure, which is going to raise their overall energy, and the meta doesn't. Looking at the energy profile then, we have benzene down here. The other two pathways are above benzene because an electron withdrawing group is going to destabilize all the cations. It's going to make that a deactivating group. But if we look, the meta goes up only a little because it doesn't have any particularly bad resonance structures, whereas the ortho and para go up a lot because they have extra potential energy caused by the bad resonance structure. So comparing the height of these two, we can see the meta would be relatively faster, and so meta products would be preferred.